In this video, we're going to analyze the graphs of functions, and we're going to find some characteristics of those graphs. For example, we're going to look at how to find domain range. We're going to find the intercepts, x and y intercepts, intervals increasing, decreasing, and constant, as well as symmetry. So test for symmetry. If we are trying to figure out whether or not a graph is symmetric with the x-axis, the y-axis, or the origin, what can we do to test for those symmetries? Well, it all has to do with substituting the negative in, the opposite. So if we substitute negative x for x and the result is the same equation over, then we're going to have symmetry with y. Symmetric with respect to the x-axis, we can substitute a negative in for y, and then we result in the same equivalent equation. Then we have respect with the x-axis. Symmetric with respect to the origin is going to be substituting negative x in for x and negative y in for y, and see if you get an equivalent equation. So let's do some examples. So let's say I'm going to test for all three symmetries. So I'm going to start with symmetry with the y-axis. That means I'm going to plug in negative x. So plugging in negative x means I'm going to do y equals negative x cubed. Well, when I simplify y equals negative x cubed, then that's going to give me y equals negative x to the third power. Because this is negative x times negative x times negative x. It's negative x to the third. Well, that is not exactly the same as y to the x to the third power. So we do not have symmetry with the y-axis. So no symmetry with the y. So what about symmetry with the x-axis? Well, that means I'm going to plug in negative y into my formula, and then I'll simplify. Well, to simplify, we would divide by negative 1. So y equals negative x to the third. And again, those are not the same equation, so we do not have symmetry with the x-axis. So the last one we're going to check is symmetry with the origin, which means we're going to plug in a negative y and a negative x and see what results. Well, negative y equals negative x to the third power. That would result in negative y equals negative x to the third power, because again, negative x cubed is negative x to the third power. Divide that by negative 1, and our result is y equals x to the third power. Well, that is the same as my original. So therefore, this has symmetry with the origin. Okay? So let's try another one. So when we plug in y equals, plug in negative x squared plus 5, and we simplify that, we get y equals negative x squared is x squared plus 5, which is the exact same thing. So therefore, this has symmetry with the y-axis. Let's check it for the x-axis. So we're going to plug in negative y equals x squared plus 5. And again, you divide by negative 1, you get negative x squared minus 5. So that does not have symmetry with the x-axis. And then to plug in both, negative y equals negative x squared plus 5. Well, that's going to give me negative y equals x squared plus 5. And again, divide by negative 1, you get y equals negative x squared minus 5. So that also does not have symmetry. So the only symmetry we have with y equals x squared plus 5 is symmetry with the y-axis. Okay, let's test number 3. We're going to plug in negative x squared plus y plus 1 squared equals 4. And then when we simplify, that gives me x squared plus y plus 1 squared equals 4, which is the same as the beginning. So we do have symmetry with the y-axis. Let's check the others. So x squared plus negative y plus 1 squared equals 4. Well, I can't simplify that to get the exact same thing out. So we're not going to have symmetry with the x-axis. And a very similar thing is going to happen when we make both of them negative is I can't simplify that out. So because of the negative y plus 1 squared, it's also not going to be symmetric to the origin. All right, let's try this last one. Y equals negative, the absolute value of negative x minus 2. Well, remember, the absolute value of negative x, whatever it is going to be a positive. It's going to be the same thing as the absolute value of x. So therefore, we have symmetry with the y-axis. Okay, when we do negative y equals the absolute value of x minus 2, I divide by negative 1. Y equals negative the absolute value of x plus 2. That is not the same thing, so there's no symmetry with the x-axis. And then when I change both, negative y equals the absolute value of negative x plus 2. When I change both, I get the negative y equals that's absolute value of x plus 2, because those are the same thing. Then I divide by the negative 1, so that's going to give me negative absolute value of x minus 2. So again, there's no symmetry with the origin on that one either. So another aspect of symmetry is identifying whether a graph is even or odd. A graph is even if it has symmetry with the y-axis. In other words, when we plug in negative x, the result is exactly the same function. An odd function has symmetry with the origin. Now, in our symmetry video, we talked about changing x and y. Here, we have a simpler test to use, and that is on a function, if we plug in negative x, and the result is a function that is exactly opposite of my original function, then we have symmetry with respect to the origin. And so that applies, kind of adds on to what we looked at when we did symmetry. So let's look at some examples of this. So let's look at this first one. If I plug negative x in, I'm going to get negative x to the 4th power minus negative x to the 2nd power plus 2. Well, negative x to the 4th power, that means multiplying negative x times negative x times negative x times negative x. That's going to give me, because there's 4 negatives, positive x to the 4th. And then negative x squared is going to give me a positive x squared. So this is going to result in minus x squared. And then this doesn't multiply by anything, so it's going to be plus 2. Now, look at your original function and look at your new function. They are exactly the same, so therefore these functions are, this function is even. All right, let's do another one. So f of negative x equals negative x cubed minus negative x plus 3. Well, again, negative x cubed is going to result in negative x to the 3rd power, because there's 3 negatives. That's going to leave it negative. Then it's going to be to the 3rd power. And then minus a negative here creates a plus x. And then I don't have anything to multiply there, so plus 3. Now compare that to the original. This is x cubed, negative x cubed, so that's opposite. This is negative x, positive x, that's opposite. But look at this last term. Look at the very last term. It's plus 3 plus 3. What that means is these are not exact opposites. They're also not exactly the same, so this would be a neither situation. This is neither even nor odd. Not all functions have symmetry, so neither is an option. So let's look at another one. F of negative x is going to be negative x cubed minus negative x. Well, negative x cubed is negative x to the 3rd power. Minus a negative is plus. And when I compare to my original function up here of x cubed minus x, negative x cubed plus x is the exact opposite. They're exactly opposite. You can see that because x cubed here is positive, here it's negative. X here is negative, here it's positive. So they're exactly the opposite. So opposite means that they are odd functions. Graphically, we can just look at them and say, are they symmetric to the y-axis or the origin? In this case, when I draw the line of symmetry there, I can see that this side of the graph is mirrored on this side. So it has to have symmetry with the y for that to happen. So this would be an example of an even function on a graph. Now, an odd function is a little bit harder because you've got symmetry with a point, the origin. So it's flipped over the origin. So this part of the graph is flipped over. Kind of think of it as being flipped over x and y simultaneously, but you notice you get that same shape when you rotate it around. And so this would be considered an odd function. All right, so graphing piecewise defined function. So what a piecewise defined function is a function that can't be written with one equation. You see this a lot in real world applications because everything can't be described with one simple equation. But if we break a situation into pieces, we can write the equation of the different pieces and then create one function out of all of those pieces. And so that's what a piecewise defined function is. When we are evaluating and graphing them, the key to a piecewise defined function is actually the domain values right here on the right. This is telling you when to apply this part of the function. So for values less than 0, we are going to apply x squared plus 1. For values that are greater than or equal to 0, we're going to apply x minus 1. So it's very key that you're looking at this domain values when you're determining which piece of the function. You will never use both pieces of the function on the same problem. Okay, you have to choose one. Otherwise, you have repeating x values, and that doesn't work. So let's look at this one. So according to this, they want me to find f of negative 1. Well, which piece of the function does negative 1 fall into? Well, negative 1 is less than 0, so it's going to fall into the piece of the function x squared plus 1. So what does that look like? That means I'm going to plug negative 1 into that piece. So negative 1 squared is 1 plus 1. That means f of negative 1 is positive 2. All right, let's do f of 5. Well, where does f of 5 fall into this function? Well, 5 is greater than 0, so it's going to fall right there in the second piece, the bottom piece, x minus 1. So I'm going to plug 5 into x minus 1, and that result is 4. So what about 0? F of 0. Well, 0 falls into the bottom portion because that's where my equal to 0 is. X is greater than or equal to 0. And so when I'm plugging this in, I'm not going to plug it into both of them. I'm only going to plug into the piece where it's equal. So that's going to be 0 minus 1 equals negative 1. We can see this on this graph. This graph over here. This is the graph of this piecewise function. Notice we have a parabola here moved up 1. We can see that it's just the left side, the part that's less than 0. And then at x equals 0, we start with the line x minus 1 that goes off to the right. So if you see, negative 1 is at positive 2. 5 is at 4. And 0 is defined at negative 1. Let's try another one. Let's evaluate this one. So we're going to try to find h of 1. So think about h of 1. Which of these domains will 1 fall into? Is 1 less than 2, between 2 and 4, or greater than 4? Well, 1 is less than 2. So I'm going to plug 1 into that particular piece, and I get 1 squared plus 3, which would be 4. Then where does 3 fall? Is 3 less than 2? Is 3 between 2 and 4? Or is 3 greater than 4? Well, 3 would be between 2 and 4. So when I plug 3 in, notice here, this one's a little bit special. Notice here, this one is 7. No x values. So h of 3 is simply 7 because I don't have anywhere to plug in my 3. And what about h of 4? Well, where is the equal to in this problem? Well, the equal to is right here on the middle, so this one also equals 7. Lastly, h of 5. Well, h of 5 is greater than 4, so we're on this bottom one. So we're going to do 2 times 5 minus 1. That's 10 minus 1 is 9. So how do we graph a piecewise function? Well, it's about graphing the two pieces. So I have two things I need to graph. I need to graph 1/2 x plus 1. I also need to graph negative x minus 1. So these are both lines. So think y equals mx plus b. We've graphed lines before. So I can graph them, first of all, first choice, I can graph them by doing slope-intercept. So my intercept here is 1. So I have the point 0, 1 on this graph. Then I have the slope of 1/2. On this equation, I have a y-intercept of negative 1. So 0, negative 1 is a point. And a slope of negative 1. But notice where my domain is. My domain is at 2. So my graph is splitting right here at positive 2. So I'm going to graph this on the less than 2. I'm going to graph this one on the left of that dotted line. I'm going to graph this one on the right. Now, you may think, well, my y-axis is not available for this point. Well, there's a couple of options you have. You can either use that point and then erase the part of the line you don't need, and I'll show you how to do that, or you can just find another point to work with. Okay, so I'm going to show you how to just graph it and erase what you don't need. So let's start with graphing this one. I'm going to graph this one in blue. So I have a point at 0, 1. There's my y-intercept. I have a slope of 1/2, so that's up 1 over 2. Well, notice that puts me on my dividing line. So the question I got to ask myself is, in x less than 2, if I'm sitting on this line, up 1 over 2, do I put an open circle or a closed circle? Well, that is not equal to. So here, I'm going to put an open circle. I can even count backwards just to get me another point if I want to. I'm going to draw my line that way. So that's the left side of my line. Now, I'll do the other one in green just to kind of let it stand out. So if I want to graph this exactly the same way, my y-intercept is at negative 1, and I'm going to count, I can count down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. So my line goes that way. But my line doesn't need to start until this point right here because it's greater than or equal to 2. So what I'm going to do is I'm going to erase everything before that. So there's the graph. Now, if you don't want to do that, what you can do is you could plug, say plug 2, get my pen back. You could plug this value of 2, so negative 2 minus 1 equals negative 2 minus 1, which is negative 3. And I can know that that's the point where I need to start. Okay, so I can either find other points that are within my domain values, or I can graph the line and then erase the part that I don't need. Let's do one more of those. So I have 3 divisions here. I'm going to put them, I'm going to highlight them this time. So my divisions are, because they're not really part of the graph, I just do this to help know where I'm at. So 0 is one of the dividing lines, so I'm going to have a dividing line right there. 2 is a dividing line, I'm going to have a dividing line right there. So I've got 3 sections of this graph. The first section is defined to the left of 0, x is less than 0. That section is defined simply as negative 1. That makes it a horizontal line. At negative 1, this does not have an equal to. X is less than 0, no equal to, so we're going to open circle at negative 1, and we're going to draw a horizontal line on the left side. So that takes care of that. Now, in the middle, I have x minus 1. So I have a y-intercept of 0, negative 1, and a slope of 1. And I'm going to draw this between 0 and 2. And notice both of those are equal to. So when I start graphing this, I'm going to shade the endpoints of this particular section because of the equal to. So 0, -1. Well, notice what happens here. That means that point that I had an open circle on is now part of the graph. And then I'm going to count up 1 over 1, up 1 over 1. And so here is the middle section. Notice that the green and blue line are actually connected. Okay, so we actually do have a point there. Now let's do the third section. For those points that are greater than 2, I'm going to graph the line starting at 0, 6, and a slope of -2. Well, notice I don't have a 6 up here. Notice that my graph stops at 5. So this is going to be one of those situations where I might want to just find a point. So let's plug in, say, -2 times 3. -2 times 3 is -6, plus 6 gives me 0. So a point within my domain that I could use is 3, 0. So 3, 0. Now you're thinking, well, what do I do next? Well, now I'm going to count my slope because I can go down to right 1, or I could go up to left 1. And remember, this is not equal to, so I'm going to put an open circle. And there's the line for that piece. So we're going to investigate increasing, decreasing, and constant behavioral functions. We call these, I often call them intervals. We're going to describe the intervals of a graph that is increasing, decreasing, and constant. And so this is your notes for this. So let me see if I can make it easier to understand. So for all x of 1 less than x of 2 on the interval I, the function f of x plus 1 is less than f of x plus 2 means that it's increasing. So the easy way to do this, other than describing it mathematically, the easy way is to look at the graph and say, is the graph going up from left to right? If the graph is going up from left to right, it is increasing. If the graph from left to right is going down, then it's decreasing. And if the graph is not changing from left to right, it's a constant. We always describe the interval with the x values. And the reason we do that is because we're describing where it is increasing and where it is decreasing. So we're going to be using those x values to describe where these intervals are taking place. Let's do some examples of this. So using interval notation, write the intervals over which f of x is increasing, decreasing, and constant. So if you look at the graph carefully, the graph from left to right is going up here. It is not changing here. It is going down here, and then it's going up there. So we are increasing on two intervals. We are constant on this interval, and then we are decreasing on this interval. And we're going to use the x value. So I need to know, first of all, that's forever. What is the x value where they change? So there's a change here, there's a change here, there's a change here, and then it goes on forever. Those are the intervals we're going to look at. So starting with the increasing, we are negative infinity because it's pointing to the left forever. So negative infinity, it stops increasing at an x value of -2. But then it starts increasing at an x value of +2. Well, that means we're going to have two intervals. So we're going to join those with a u. And it's going up from 2, and then we have an arrow at the end to infinity. And what about your decreasing interval? Well, the decreasing interval starts decreasing at 0 and stops decreasing at 2. And then your last one, your constant, starts being constant at -2 and stops being constant at 0. Now notice I used only the x values. Notice I only use parentheses. The only time we won't use parentheses is if we have an endpoint that we're using to describe. But for the most part, in general, we always use parentheses when describing intervals increasing, decreasing, and constant, because those turning points are the points where they change from one of those to another. You're not doing either because there's a change at that exact point. So let's do another one. So if you look on the left, it starts with decreasing. So this section is decreasing. But then you look and you see this section, it's not decreasing at the same rate, but it's still going down. And then you see this section is also decreasing. So notice that we don't have any constants and we don't have any increasing. It decreases over the whole graph. So how do we describe that? Well, we describe that as it's decreasing from negative infinity to positive infinity. It doesn't have these other two types of intervals. Another characteristics of graphs are the relative minimum and maximum of a graph. So relative minima and maxima means that over a small interval section of the graph, you have a highest point or a lowest point, okay? So highest point would be relative, lowest point would be, highest point would be a relative max, lowest point would be a relative minimum. Now, these are different from what we call absolute or global minimums and maximums. Okay, absolute or global means over the entire graph. Okay, so if it is the absolute highest point or the absolute lowest point of the graph, that's the absolute or global minimum or maximum. The relative, or sometimes you'll hear them referred to as local, are those that we find over this smaller area. Lots of times these are going to be our turning points. Every turning point is a relative minimum or maximum. So that's how you have to describe them. So here's an example of finding relative minimum or maximum points. Okay, so this graph has one of each. So let's look at that. So let's see, there is a relative minimum here. Why is that a relative minimum? It's a relative minimum because at that point, which happens to be -2, -1, is the lowest point on an interval around -2. Okay, this point is the lowest point on an interval around -2. Okay, now how do we describe that? That means that x equals -2, the function has a relative minimum value of -1. So here's what I like to say. Where is your x? What is your y? And why do I say that? It's because anytime we are describing where something happens on a graph, we're always going to be using the x value of the coordinate. Anytime we're discussing where something happens on a graph, we're describing that using the x coordinate. Anytime we're asked what a function value is, what is the function value? That is the y. So what is the function value? What is the minimum? What is the maximum value? Those are y coordinates. Where is the minimum? Where is the maximum? Where is the x? Okay, so let's look at the next one. Let's find the maximum. So let's describe this point. So that is a relative maximum. The reason that particular point, which happens to be 0, 1, it is the highest point on a small interval around x equals 0. That means at x equals 0, where's the x? The function has a relative maximum of 1. What is the y? So let's do another one. So let's identify where our points are. So we have a relative minimum here. We have a relative maximum here. Then we have another relative minimum here. So let's just start on the left with that first one. We have a relative minimum. Where is the relative minimum? Well, the relative minimum is at x equals -1. And it has a relative minimum value of x equals -2 because that point is -1, -2. So let's look at this other, okay, so they've got minimum the minimums together. So let's look at the other minimum. That point is 4, 0. So at x equals 4, there is a relative minimum value of 0. Then we have at x equals, so let's figure out what this point is. It is 2, 3. So at x equals 2, there is a relative maximum of the value 3. Again, where is x? What is y? So what about this one? Relative minimums and maximums. Well, it goes forever in both directions. So we're going up forever, we're going down forever. It doesn't have any turning points. So without an ending point or a turning point that can be a minimum or a maximum, we actually have none. This one actually has no minimums or maximum values. And it's possible for a graph not to have any. In this video, we're going to perform operations on function, including adding, subtracting, multiplying, dividing, and a new operation called composition of functions. We're also going to be looking at how to figure out the domains of our results. So let's start with the 4 basic functions. This is easier than it probably looks based on what you see here on the screen. What these notes are giving you is that if I want to add 2 functions together, I'm going to take the 2 functions and I'm going to add them together. This means we're going to combine like terms. So remember, like terms means they have the same variable with the same exponent. If they don't have the same variable and the same exponent, then we just write it out all the terms. Subtraction is the same thing. The big thing we need to watch out with subtracting 2 functions is if the second function has multiple terms, we need to be able to distribute the negative to all the terms in the second function. Multiplying is distributing, so we're going to multiply f of x times g of x. We're going to distribute from one term to the other. Dividing many times is just writing one function divided by another function. The big thing is, and this is where that domain is going to come in really strong, is that we create a restriction to the domain when we put a function in the denominator because that function in the denominator cannot equal 0. So we could create a restriction that wasn't there in the original functions just by putting a function in the denominator. So let's review our function notation while throwing in some of these operations that we're looking at. So here we're going to just kind of remind you of what function notation is and how we work with it. So let's start with number 1, f of negative 3. Well, f of negative 3 means I'm going to refer to the f function, and I'm going to plug negative 3 in for x. So f of negative 3 is going to be negative 3 squared minus 3 times negative 3 plus 1. Notice that I have put negative 3 everywhere there was an x. That's what we mean when we do function notation. When I calculate that, my answer is 19. Go back up here and get my pen. Okay, let's do g of 4. Well, g of 4, I'm using the g function. Here's the g function. And I'm going to plug 4 in for x. So let's go up here and plug 4 in for x. So g of 4 is the square root of 8 minus 4. Okay, which 8 minus 4 is 4, and the square root of 4 is 2. So that would be my answer. So let's look at number 3. I'm back to using the f function. So f of a plus 1 means that I'm going to put a plus 1 everywhere there's an x. So in all those places. So you're going to do a plus 1 squared minus 3 times a plus 1 plus 1. Now this means we're going to actually have to multiply this a plus 1 out. Remember, it's not just a plus 1, a squared plus 1. We actually have to distribute. The result of that is a squared plus 2a plus 1. And then when I distribute that, I get minus 3a minus 3 plus 1. Then when I combine like terms, I get a squared minus a plus 2. Now let's go back to the g function again. The g function, remember, there's where the x is, so 10 goes in there. So the square root of 8 minus 10. Well, the square root of 8 minus 10 is the square root of negative 2. And we know the only way we can write that is I square root of 2. Now let's go and look at this one, because this one is actually asking me to do f minus g. So I'm going to do f minus g. What that means is I'm going to do f of negative 8 minus g of negative 8. Well, what is f of negative 8? Well, f of negative 8 is when I plug negative 8 into the f function. So negative 8 squared minus 3 times negative 8 plus 1. So that is my f function. Then I'm going to subtract what happens when I plug in negative 8 into my g function. So square root of 8 minus negative 8. So what does that equal to? Well, f of negative 8 turns out to be 89. That means you're doing negative 8 squared, and then you're going to multiply negative 3 times negative 8, which is positive 24, plus the 1. So you're going to get 89 out of that. On the other side, the square root of 8 minus a negative 8, that's 16, square root of that is 4. And so then I'm going to subtract those two values and get an answer of 85. So let's do g times h. So we're here. G is the square root of 8 minus x. So we're going to have to do the square root of 8 minus 0 times h. H is over here. So we're going to do 2 over 0 plus 1. So we're going to multiply those two things together. So this is multiplication. Well, what is the square root of 8 minus 0? Well, the square root of 8 minus 0 is the square root of 8. And what is 2 divided by 0 plus 1? Well, 2 divided by 0 plus 1 is just 2. So when I multiply those results together, I'm going to get 2 square root of 8. Now, you can simplify the square root of 8. It's really not the focus right now, but remember, just kind of as a gentle reminder, we can break this down into 4 times 2, and then 4 broken down into 2 times 2. So I have a pair of 2's. So the square root of 8 will actually simplify into 2 square root of 2. But then I need to multiply by 2. So my actual answer is 4 square root of 2. Just in case you have to simplify that all the way down. And then lastly, I have h of negative 1. Well, that means I'm going to do 2 over negative 1 plus 1, which gives me 2 over 0, and that is an issue. So that particular thing is not defined. It does not exist, or you can say that it's undefined would be your answer. So let's do some more evaluating, but this time we're going to talk about what's the domain of the result. Okay, so we're going to start with r minus t of x, which means that we're going to do, let me change that color. We're going to do r of x minus t of x. So what is r of x? Well, r of x is x squared plus 3. That's r of x. We're going to subtract t of x, which is x plus 4. Now remember, when we are subtracting, we have to distribute that negative. So what we get is x squared plus 3 minus x minus 4. So the result of this, when I combine like terms, is x squared minus x minus 1. Now, let's talk about what's the domain of that. Well, if you look, the domain of x squared plus 3, that's a parabola, and we know the domain of a parabola is all real numbers. T of x is x plus 4. The domain of that is all real numbers because it's a line. So when we subtract, we actually don't change anything. We don't create a restriction that's not already there. So therefore, the domain of this result is actually still all real numbers because we haven't created any kind of restriction. So let's look at another one. let's look at number 9. R divided by T of X. That means we're going to do R of X divided by T of X equals, what is R of X? Well, R of X is X squared plus 3. What is T of X? X plus 4. So there's my quotient. But what is my domain? Well, the thing is that both of these functions have domains that are all real numbers. But when I put that T in the denominator, T plus 4 can no longer be 0. So now I have a restriction that T can no longer be negative 4 because it's in the denominator of a fraction. X plus 4 is now in the denominator. So I have to write my interval notation excluding negative 4. So that's going to be negative infinity to negative 4, unioned with negative 4 to infinity, because we have to exclude the value of negative 4. So let's look at the next one, S times T of X. So this is going to be S of X times T of X. So S of X is going to be 2 over X times T of X, which is X plus 4. So best I can do there is to do 2X plus 8, distribute that 2 over the X plus 4 over X. Okay, now we got to think about what's the domain of S of X. What the domain of that, since X is the only thing in the denominator, is X cannot be 0. That doesn't change when I multiply by X plus 4 because X, all that's in the denominator is still just X. So X can't be 0. So what does that look like in interval notation? Well, we stop our interval at 0. So we're going to negative infinity to 0, union with 0 to infinity, and use those parentheses to indicate that we're not going to include that value. We have an application of using operations with functions called the difference quotient. Anyone who's going to follow college algebra with other math courses, particularly calculus, this difference quotient becomes extremely important. So the difference quotient is actually simply finding the average rate of change, the slope between 2 points on a graph that's not necessarily a line. So we know in a line that all of your slopes are the same. So you have a constant rate of change. Well, all graphs have slopes, but not all graphs have the same slope. Only lines have the same slope no matter where you're at on the graph. So what we do is we have this average rate of change idea, and it is found using the difference quotient. It is basically the change in y over the change in x. We have a formula here, but it really is just a slope formula given this kind of diagram here you've got, where you've got 2 points on a graph, x, f of x, and then x plus h and f of x plus h, and you're finding the slope between those. So this is called the difference quotient. It uses the same ideas that we've been doing with the operations of functions, and we're putting it all into finding the slope between 2 points on any graph, also called the secant line. So let's do one. So the first thing we're going to do, anytime you pick up a difference quotient problem, the first step is to just worry about finding f of x plus h. That means I'm going to plug x plus h into the x in my function. That means I'm going to do 5 times x plus h minus 2. So my function is f of x equals 5x minus 2. So when I'm trying to find f of x plus h, it becomes 5 times x plus h and then minus 2. So I'm going to distribute that 5. So f of x plus h is 5x plus 5h minus 2. Now, with that, I can now fill in my difference quotient because it's f of x plus h. So that's 5x plus 5h minus 2 minus f of x, which remember f of x is 5x minus 2. And remember, when we subtract, we have to distribute. And we're going to divide that by h. So let's start out by simplifying the numerator. So I need to distribute that negative. So that's going to be 5x plus 5h minus 2 minus 5x plus 2 all over h. Then if you notice, I have some like terms. 5x minus 5x, negative 2 plus 2 all cancel out. And it leaves me with only 5h on the top. So 5h divided by h is 5. So the difference quotient for the f of x equals 5x plus 2. The difference quotient gives me 5. Just so you know, your difference quotient doesn't always result in a single numerical value. So let's work this example so we can see that it doesn't always result in just a number. So the first thing we're going to do, as before, f of x plus h is the first thing I'm going to do. So my function is f of x equals x squared minus 3x plus 8. And I'm going to change the x's to x plus h. So that means I'm going to have to do x plus h squared minus 3 times x plus h plus 8. So x plus h squared, again, you're going to have to, if you need to, you write that out and multiply it. For the sake of time, I'm going to tell you that it's x squared plus 2xh plus h squared. Then I'm going to distribute minus 3x minus 3h plus 8. Now, if you look really hard, there's really not any like terms there. That is f of x plus h. There's not a whole lot of combining I can do. And so now to find my difference quotient, I need to do f of x plus h. So that's x squared plus 2xh plus h squared minus 3x minus 3h plus 8 minus x squared, or f of x. So that's going to be x squared minus 3x plus 8. All divided by h. So I'm going to distribute this negative. So lots of writing here. X squared plus 2xh plus h squared minus 3x minus 3h plus 8 minus x squared plus 3x minus 8. All over h. And then look at what you get there. I have, combining like terms, I have x squared minus x squared, that's 0. I have negative 3x, positive 3x, that's 0. And positive 8 minus 8, that's 0. So what am I left with? I am left with this 2xh plus h squared minus 3h. So what can I do? Well, all three of these terms have an h. So we're going to factor out the common factor of h. That gives me 2x plus h minus 3 divided by h. So now those two divide out. So my final answer is 2x plus h minus 3. It's a lot of writing. You'll get the patterns of things that happen, and you might be able to shorten the writing of it. But in these first instances, you need to write all those steps out, or I'm telling you, you're going to miss a term. So let's look at one more composition before we look at decomposing functions. When we compose two functions and then we want to find the domain of that, one of the first things we need to look at is the domain of the original functions. So when I see f of x equals 3 over x plus 2, I know that that's a fraction, so x plus 2 cannot equal 0. So what makes x plus 2 equal 0? So in this particular case, x cannot be negative 2. In g of x equals 3x minus 2, that's a line. So in this case, that's all real numbers. I don't have to worry about any kind of restrictions there. So when I start to compose them, I have to take in consideration two things. First of all, what is the domain of the inside function g of x? Well, it's all real numbers, so I don't really have any restrictions to have to worry about with that domain. But the second piece is what parts of the range of my 3x minus 2 are going to be a problem in my f function, my outside function of 3 over x plus 2. Well, that would be any value that would make this 3x minus 2 equal negative 2, because negative 2 can't happen. So what I do is I find out 3x minus 2 equals to negative 2, that value that's restricted from the f function. So plus 2, 3x equals 0, so x equals 0. So what I know is that when I compose these functions, since my inside function is all real numbers, but my outside function has a restriction, in the end, x cannot be 0. That's going to be my domain of my composition. Now, I also want to show you how to figure that out without having to do these steps in advance. So let's look at the composition. So if I'm doing the composition of f of g of x, then that's f of g of x, meaning I'm going to take the g function, 3x minus 2, plug it into the f function. So that means I'm going to do 3 over 3x minus 2 plus 2. Well, minus 2 plus 2 gives me 0, so 3 over 3x, and then 3 over 3x reduces to 1 over x. So my composite function is 1 over x. Notice that the domain of my end result, my 1 over x, is x can't be 0. I also figured that out using my original functions. So you can do it either way. The one thing I will warn you about is you have to include any restrictions of the domain on the original functions. We happen to not have any on this particular example. So my domain here is going to be negative infinity to 0, union with 0 to infinity. Remember, that's how we cut off particular values. So the second part of this particular slide is that I want to decompose functions. And I've been talking about in other parts of this lesson how we look at a composite function as an inside function and an outside function. When you are decomposing, you need to take and consider what's on the inside and what's on the outside. So for me, what I look at is what is on the inside of this function. Well, the inside of this function is 3x minus 7, while the outside is the square root of x. So when I decompose these two functions into two functions that will result in the answer of the square root of 3x minus 7, what I'm going to do is I'm going to write the functions based on the inside function, meaning g of x is going to be my 3x minus 7, and then my outside function, meaning that f of x is going to be the square root of x, so that when I compose them, 3 of x would go inside of the square root to give me the result I wanted. I can do the same thing with this number 18. H of x equals x plus 1 in parentheses cubed plus 8. Think about what's inside. What's the most inside part of this function? The most inside part of this function is x plus 1. So that's what I'm going to make g of x. Okay? What's the outside part of the function? Well, the outside part is my parentheses cubed plus 8. So that's what I'm going to make my outside function f. It's going to be x cubed plus 8. And that will give me the two functions I need to create this one composite. So let's look at how to find these operations graphically. So I have a blue function here that is f of x and a red function here that is g of x. And I want to find in my first one f minus g of 3. Well, f of 3 minus g of 3 requires me to find two function values. The first one being f of 3. So f of 3, I'm going to go out to x equals 3. And then I'm going to go find the graph at x equals 3, and that graph is at 4. So f of 3 is going to be 4. Now I'm going to find g of 3. Well, g of 3, again, go out to 3, and now I'm going to go look up to the g function, the red function, and that is at 3. So g of 3 is 3. The result of my operation of subtraction would give me 1. So f minus g of 3 equals 1. What about g divided by f of negative 2? That means we are going to find g of negative 2 divided by f of negative 2. So again, I'm going to go to my graph. Well, what is g of negative 2? Remember, g is the red graph. Negative 2 is here. Let's find what that equals to. G of negative 2 is negative 4. So I'm going to make that negative 4 divided by f of negative 2. So again, negative 2 is here. F of negative 2 is positive 2. So that's going to be positive 2 here. And negative 4 divided by positive 2 is negative 2. So G divided by F of negative 2 is negative 2. So what about the composition of G of F of 1? Remember, that means G of F of 1, meaning I'm going to find F of 1, the inside function, and then I'm going to plug that into the G function. So let's start with the F of 1. F of 1 is my blue function. 1, x equals 1 is here. F of 1 would be 2. So that means I would have G of 2. So I'm going to plug 2 into the G function. So let's see what that is. Red is G, so I'm going to go to 2. And 2 is up here at 4. So G of 2 is 4. So the composite G of F of 1 is 4. All right, look at F of G of negative 3. That means we're going to do F of G of negative 3, meaning I'm going to have to go find G of negative 3 first. So G is my red function. So negative 3, 1, 2, 3. It's at negative 4. So I'm going to go plug that in. F of negative 4 equals, and now I'm going to go back to my graph and say, what is F of negative 4? Well, negative 4 is here, and the G function would be here at negative 2. So that equals negative 2. So F of G of negative 3 is negative 2. So what we're doing is we're going and finding the points on the graph that we need to complete my operation. So the last one is F of negative 3. Now, I know they use the same function twice, but it's okay. We're still going to work it the same way. So when I do F of negative 3 here, I'm going to go to negative 3, 1, 2, 3, and F of negative 3 is 0 because that's where it's at. So F of negative 3 is 0. So now I'm going to find F of 0. F of 0 is F of 0 is 2. So the answer is 2. So we can plug a function into itself. That's a possibility. So let's look at an actual application problem here. A party balloon is being filled with helium. As the balloon is filling, the radius of the balloon is changing at a rate of 3 inches per second. Write a function that represents the radius of the balloon, r of t, after t seconds. Well, keep in mind the balloon is increasing at a rate of 3 inches per second. So r of t, the changing of the balloon, is 3t because it's 3 inches per second. Write a function that expresses the volume of the balloon with respect to its radius. And so this is a formula. The volume is, let me write it in, we want to write it in notation form. V of r equals 4/3 pi r cubed. Now that is a formula that you can find online or in your textbooks. So then it says evaluate the composition of V and R, V of R of t. So we're going to be finding V of R of t and explain its meaning and context. So what is V of R of t? Well, that means I'm going to take R of t, 3t, and I'm going to plug it into R here. So 4/3 pi times 3t cubed. Now we got a little simplifying to do because 3t cubed is 27t cubed. And when we multiply 4/3 times 27, we're going to get 36 pi t cubed. Now, what is that actually finding? Well, it is actually finding the volume with respect to the time. So after how many seconds, what is the volume of the balloon going to be? So my results of A, 3t, is how the radius is going to be changed after so many seconds. B is the volume as the radius is changing. My composition is actually going to be the change in volume according to how many seconds have passed, so with respect to time. So then it says to evaluate V of R of 2. That means we're going to do V of R of t of 2. Put 2 in its place. Well, I've already found V of R of t. It's 36 pi times t cubed. So that's going to be 36 pi times 2 cubed, which is 288 pi, which is approximately 904 cubic inches. So the meaning is after 2 seconds, the volume of the balloon will be 904 cubic inches. And so we can put functions together using this composite so that we can use different formulas to find different information.